Well, thank you, Lydia, and thanks to all of you for getting back from your lunch early. I'd like to talk to you a little bit about a very theoretical problem I've been looking at that had a very practical inception. So how many of you, just as a show of hands, how many of you have ever worked with the Baxter robot? And lower your hands if you don't. Wait, keep your hands up. Now keep your hands up if you understand its kinematics fully. Yeah, so yeah, me too. So just as an example of this, I was working with a Baxter robot for the Amazon Picking Challenge, and we start to see a bunch of weird things. You can move the arms of the robot around, you can try to get it to perform certain paths, and we were just having a lot of trouble. None of the students that were working on the project really understood what the robot could and could not do, and even when we ran this with motion planners, they'd come up with very strange paths that didn't really explain, we couldn't explain exactly why it was doing the things that it did. So you could see that it took this kind of roundabout path to get out from the shelf into this bin. And so I wanted to start to think about this problem, think about the problem of kinematics a little bit more deeply. And so I'm going to introduce the worst pun of the Wafer conference, but I wanted to rethink inverse kinematics from the very beginning. So basically all of us know what forward kinematics is. You have a map, a functional map, from any configuration to a Cartesian output variable, some workspace variable. So this is a P is equal to F of Q. And what we know from Robotics 101 is that this is a bit of a nice, well-defined function, but the inverse is rather less well-defined. So for example, if you have joint limits, then you can have, let's say we have a two-link robot here with joint limits. There's a region on the top of this reachable workspace in which you can only reach it with elbow down configurations. In the bottom half of this reachable workspace, you can only reach those points with elbow up configurations, and in the middle there's some multiple solutions in that middle region. And so the issue with this kind of problem is that if you have a path that goes between the top region and the bottom region, there's no continuous path in configuration space that executes that Cartesian space path unless that path were to pass through singularity of the robot. And so we could start to think about questions like, well, if n is equal to 3, if we have 3 joints, could we possibly solve this path? And this brings us to the question of redundant robots. So let's suppose that we have more joints than we have Cartesian variables. The problem of redundancy resolution is coming up with a continuous configuration space path to execute a given Cartesian path. And so people have looked at this problem in terms of local strategies to try to avoid getting into local minima. So if you just try to, say, follow some sort of path with a local optimization method, then you end up tending to arrive into local minima and not being able to make progress along that path. And so people have worked on looking at the entire path and trying to find a continuous joint space path about that configuration space path, and that's called Pathwise redundancy resolution. So several people have looked at that problem. And so I wanted to pose the problem of whether or not all workspace paths, given a starting configuration, whether all of those paths had solutions across the entire workspace. And this is kind of interesting. So if you think about pathwise redundancy resolution, you go from one Cartesian space point to another. If you were then to perform another pathwise redundancy resolution and go back to the starting point, you're not guaranteed to, one, either be able to make it, and two, you might not end up at the same configuration that you started at. And so this might end up getting you stuck in various ways. So very few people, I could only find one other example in the literature where people were studying whether or not a global redundancy resolution existed for a given manipulator. And so a global redundancy resolution would be to have for each Cartesian space point a single configuration, and also to have that mapping be a smooth mapping so that you can end up with continuous paths as you interpolate through the Cartesian space. So this is also a pseudo-inverse problem. So many of you know what a pseudo-inverse of a matrix is, but a functional pseudo-inverse is somewhat similar. So given a function over some domain, the pseudo-inverse of that function is basically if we flip these two axes and we try to find a mapping from the range of that function back to its domain, such that if we map x through f, the pseudo-inverse maps that result y back to x. So this is an example of a pseudo-inverse of this function, this kind of darkened line here. And you can see there's many discontinuities here in this function. And so perhaps a better pseudo-inverse might look something like this, where you have fewer discontinuities, or ideally we'd have a continuous pseudo-inverse that goes through without any kind of discontinuous jumps. So I posed these couple of questions. Does a continuous pseudo-inverse exist for a function? And if not, can you maximize continuity? And third is also quite important for redundancy resolution for robots. We want to be able to do this for a multivariate function. We want to have both the input and the output of this function f be higher dimensional than 1. So we can start thinking about this pathwise redundancy problem as a function from a one-dimensional space to an n-dimensional space. So if we look at the path parameter on the x-axis, the pathwise redundancy resolution problem says, well, if we think about at every point along this Cartesian path, we have a certain self-motion manifold where that Cartesian goal is met by the configurations in that manifold. This could also be a manifold with boundaries, if we take into account joint limits and other kinds of feasibility constraints. And the goal is to try to find a path within this manifold from the left side to the right side. So something looking like this. So if we want to then extend this to a higher dimensional problem, I proposed a roadmap method to doing this. Rather than having a single path, what I start out with is some sort of roadmap on the workspace. This is a workspace roadmap. In this case, it's a grid, although you might also think about other kinds of, say, randomized roadmaps as well. But the key thing is that the algorithm that we're trying to seek is something that resolves all of the workspace paths simultaneously with paths that basically form a sort of network on this roadmap. So the way that this is done is if you think about this is a kind of three-dimensional plot. On the XY axis is a workspace grid. This is a 3x3 set of points. And on the vertical axis is the set of self-motion manifolds, basically configuration space of the robot. And so what I do is I sample each of the self-motion manifolds at each of these workspace points and make sure that each of those satisfies the inverse kinematics constraint here, or the forward kinematics constraint. I then connect each of the configuration space edges and try to figure out whether there's a feasible path between those using some local planar. If there exists one, then I add it to a configuration space roadmap, and basically we have this roadmap and configuration space connecting many points arranged on this workspace grid. One of the things to note is that now we want to try to find a single configuration space point for each of those workspace points, such that you have essentially a kind of sheet through this workspace. Essentially, we're trying to do like a sheet fitting problem rather than just a single path planning problem. So you can think about this as an n-dimensional analog of path planning. So rather than using Dijkstra, you have to do something else. And it turns out that this ends up being a constraint satisfaction problem. And so you can formulate this with variables being the assignment of workspace points to configuration space points, matching the constraints that the edges between each adjacent workspace point should be in the configuration space roadmap. If you found a solution, then this would be a global resolution of the entire workspace roadmap. In the more common case, you can't find a global solution, and you end up wanting to minimize the number of disconnections, minimize the number of unsatisfied constraints in the CSP. This is a MIN-CSP problem, which is also studied quite a bit, but relative to the kind of traditional kind of literature on MIN-CSPs, the problems that we observe are typically much larger than the ones that are efficiently solvable, and in fact, the kind of packages that I downloaded just would not work to solve these problems. So we propose a few heuristics to try to solve this problem, and it turns out we do pretty decently well. So some of the results. I'm really fascinated with the results that come out of this algorithm, which is really nice when you usually devise an algorithm because you know what results you want. I don't know what results I'm going to get every time I run this thing. So for a 5R planar problem, this is kind of a random walk on the workspace graph here. So the gray configuration is the solved configuration, and the red one is what results from a direct point-to-point interpolation between two workspace points resolved using a pointwise resolution. And you can see that the red configuration gets stuck in quite a few points. And also you can notice that these magenta boundaries are actually the boundaries of, they're visualizations of the boundaries of disconnection between these workspace nodes. And you can see that there's kind of these two lobes where the joint limits are preventing you from going from one side to the other. And there's also this kind of seam in the middle where the arm has to flip from elbow, basically curling down to curling up. Interestingly, if you put this into a 20R problem, this is kind of an elephant trunk looking thing. Most of those boundaries go away. There still has to be a few other boundaries, but they get quite kind of localized in just one part of this optimized redundancy resolution. Extending this to 3D, apply this to Baxter, and you get these really nice, really interesting looking results. These boundaries are basically above the robot's shoulder. And basically this means that you can't really pass from this side to that side without going down and around. This is only a three-dimensional constraint. I looked at the fixed orientation constraints as well. So if you thought about fixing the orientation of the hand straight down, you get actually quite a nice workspace of this robot, which is basically the kind of natural thing that you see in all of the Baxter videos. It's always pointing down. But you do have this kind of issue underneath the armpit of the robot, and basically what this means is that if you want to go from the back to the front of the robot, you end up having to go down and around this kind of boundary. Interestingly, if you look at the forward orientation of the hand and you looked at this 3D workspace, you get this weird boundary right in front of you. So in order to go from a hand straightened out configuration to one that's more close to the body, you end up having to do a kind of reorientation to get there. Interestingly, we looked at the Kinova JACO arm, which is a 6-degree freedom arm, but it also has three continuous rotation joints, and basically it's continuously resolvable globally. And the nice thing about this continuous resolution is that it actually gives you a better solution than local methods, even though this is globally resolvable. You can see that this red configuration, which is the straight line interpolation, sometimes gets stuck in joint limits, and so the global resolution does not. So if you wanted to do teleoperation of the JACO without getting into weird configurations, this is the perfect solution for you. I also have this JPL Robosimian robot. It has a rather unusual kind of kinematic structure for its arms, and you can see that this redundancy resolution has a lot of discontinuous boundaries, which kind of goes along with some of the experience that we've had with working with JPL and so on. And you can start to see the reason why is that this arm has to be really contorted in order to get from one point to another. So in terms of final kind of wrap up, so some of the issues that we have to still look at are sampling artifacts. We want to extend this to 6-dimensional workspaces and so on. There's also a generality of this beyond IK to other domains. And also if you have any robots that you want me to test this on and generate these pictures for you, I'd be glad to do that. So I'll just leave you with this picture and I'll take your questions.
Thank you. Thank you, Kris. Juan Cortez is the first responder for this paper. So, Juan.
Thanks. So, very nice talk, Kris.
Thank you.
So, I have first a comment and then a question. So, the comment is that I actually disagree with something that you mentioned at the beginning, saying that there have been a few works about global redundancy resolution. Because actually, if you think of it, the problem can be formulated as a closed chain planning problem. And for this, there are several works that you can apply. So the formulation is very similar, actually. So this is my comment, think of it about. Mm-hmm. And my question is, reading the paper, so I like a lot this work, but there is something that I dislike, and is that it relies, I guess, this is my guess, the performance relies a lot on the function that you check if two points can be connected, what you call the visibility check. And what you are doing is a simple discrete test, and there is a parameter epsilon. And my guess is that the performance of the method depends a lot. If epsilon is very small, then you need a lot of computing time. And if it's large, then you can jump across singularities. So do you have an idea about how to set this parameter?
Well, there's actually going to be two parameters. The first one is the workspace resolution, and the second one is this checking resolution on the individual workspace edges. And I would say that I venture to guess that as the workspace resolution decreases, the effect of that epsilon is also going to basically diminish. So hypothetically, you wouldn't even need that if you had a fine enough workspace roadmap. Now, that said, it's very tricky to define, well, basically to compute these graphs with very fine workspace roadmaps, and basically it scales with the exponent of the dimensionality of the space.
Okay, maybe just a big comment about this. Have you think about using numerical continuation methods to solve this?
I haven't thought about that myself, but I think that would be an interesting way of doing it. And actually, in fact, some of the older work did end up using continuation methods to try to solve these problems. Yeah.
Okay, thank you. We have a question at the back. Can you pass the microphone, please? I cannot see.
Yeah, thank you. So for each workspace point, you stack essentially all possible islands in the configuration space that can map to that workspace point. How do you enumerate all of them?
How do you enumerate those samples? Or
yeah, the workspace, the configuration space islands corresponding to that workspace point.
Yeah, so those are done through random sampling. So with random sampling, then solving an inverse kinematics problem. I've actually looked at. I have a student looking at trying to map out those islands a little bit more intelligently. There's some people who have done this analytically with simple robots, but we're looking at ways of taking more samples per point and doing it in a computationally efficient manner. Basically building roadmaps.
Can you guarantee that you don't miss any?
No, that's one big issue. So with more samples, you'll have a lower likelihood of missing some, but right now it's just an approximation.
Okay, let me ask our next speaker to start setting up while we take one more question. I think Mark raised his hands first.
Yeah, so with your approach, you're extracting one manifold out of the C space that covers your workspace. But there may exist many manifolds, right? And you're maybe, depending on your collision and scene, you may actually prefer one over the other. Can you extract all of them that are essentially sort of equivalent and sort of have a stratified manifold?
So it's going to be a combinatorial problem because if you have, it's going to be a combinatorial problem because there are many different alternatives that you might choose. But if you wanted to say do some sort of homotopy enumeration, that would be a very interesting problem. I think if you're interested in looking at that, I'd be glad to talk to you about it.
Okay.
Yeah. And Ross, do you have a short question?
Yeah, I was just wondering,
Make it short.
is it possible to design where those pink boundaries land so that you could have better motions in the relevant workspace?
That would be really interesting. I mean, certainly you can run a MIN-CSP type of thing with weighted costs. And I think if you were to assign costs in different areas of the workspace, you could kind of design that. Yeah.
Okay. Kris, I will stop you here. Thank you very much.